Thank you for joining today's WebGL and WebGPU Meetup. Joining us are Ken Russell from Google, Kelsey Gilbert from Mozilla, Ricardo Cabello, and John Anderson from Google. First, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we'll share the link along with the slides and the recording on the events page. At the end of the session, please complete the short survey form to help us better design future events. On today's agenda, Ken Russell and Kelsey Gilbert will give us updates on the latest from WebGL and WebGPU working groups. Following the updates, Ricardo Cabello will show us how Three.js is working towards adopting WebGPU. And John Anderson will lead us on a technical journey through 5 years of Google Earth on the web. Now let's start the meetup with Ken Russell, chair of Kronos's WebGL working group. Ken?
My name is Ken Russell from Google. Kelsey and I will be giving updates on the WebGL and WebGPU APIs. So the first request is please join our communities. On the WebGL side, Kronos hosts the WebGL developers list and the public WebGL mailing lists. These let you talk about using the API and questions about the development of the API itself. You can reach browser implementers in real time on the WebGL Matrix chat room, and there's a lot of cool content showing up every day on the WebGL hashtag on Twitter. So from the WebGL side specifically, we got a bunch of little stuff to talk about, so jumping right in. Let's see here. We've had many additions over the past couple of months to the WebGL extension specifications and conformance tests in a bunch of areas around provoking vertices, uniform indice fetching, pixel local storage, which is an exciting new development, immutable textures with compressed formats, a bunch of stuff. So thank you to everyone in the community who contributed these improvements. There have been various smaller bug fixes to all browsers' WebGL implementations, and one of the more exciting API aspects is that we're supporting wide color gamuts with WebGL rendered canvases in multiple browser implementations. So finally, you'll be able to target better these newer vibrant displays in newer machines and monitors, newer laptops and monitors. So getting into the meat of things, Chris Dalton from Rive is developing an angle shader pixel local storage extension for WebGL. And this extension abstracts over multiple implementation approaches and gives you programmable blending functionality, finally. The implementation is complete in Angle, and it's ready for prototyping in browsers. There's a bug link that you can click here if you're interested in following the development. Chris just gave us a staggering demo at the WebGL working group this past week, which will promise dramatic performance improvements for many use cases. So we're very, very excited about the progress on this. The provoking vertex extension provides control over which vertex initiates a triangle or other primitive. And the availability of this extension, if you see it, if you can query for it and turn it on, it basically implies that it should be used for best performance. So by default, you'll have the last vertex being the provoking vertex. But if you see this extension available in your implementation, you really should fetch it and change the default to the first vertex. That will pretty significantly speed up your applications on multiple backends. So we really encourage you to start using it in your applications, especially if you're doing things like transform feedback. Some other new exciting news. There is now, thanks to Alexei Knyazov, a clip cull distance extension draft, and this provides hardware clip and optional cull distance support. For some applications, this can give you a pretty dramatic speed up again for your rendering use cases. So it basically gives you per primitive clipping and culling, and it avoids the expensive fragment discard where you're basically going to do a bunch of useless work. The extension is actually present in draft form right now in both WebKit and Chromium. So we encourage you to please try it in your apps and provide feedback to the browser implementers through the mailing lists that have been discussed earlier. And these slides are already available at the short link on the bottom, by the way, in case you need to get in touch with us. Another exciting extension, also proposed by Alexei, is Polygon Offset Clamp. And this basically helps your shadow maps get better quality at the edges where your the steepness of your polygons may be really high. So it's a pretty trivial change. You just call a slightly different API that provides the clamp value, and then your polygon offset will be much more robust in a bunch of different situations. So we would encourage your feedback. We're going to try to just get this in draft form and prototyped in browsers so that you can try it out yourselves. And finally, there's progress still on Engle's Metal backend. This is used by WebKit's WebGL implementation on macOS and iOS, and soon Chromium's on macOS. And we're proceeding toward shipment in Chromium. Some recent fixes of note that we've done some performance improvements for the motion mark benchmark in particular. We've disabled the Metal backend on unsupported older GPUs, fixing some rendering corruption and allowing it to basically be rolled out to everyone. And some progress on dual GPU support on the dual GPU MacBook Pros, Intel CPU based. We're nearly there. The one remaining concern and blocker for Chromium is a startup time regression due to losing the compiled shader cache, and we're collaborating with Apple engineers on this. And that's it for the WebGL updates. So Kelsey, would you like to keep going with the WebGPU ones?
Yeah, let me steal the screen real quick. Can we see that? I'm going to assume, yes, perfect. Hi, I'm Kelsey Gilbert. I'm one of the co-chairs of the WebGPU group at the W3C, and this is our update. If you haven't heard of us, we're an upcoming modern graphics API for the web, successor to WebGL. Lower overhead API, and we're trying to make sure we have a foundation for future features like bindless ray tracing and multi-threading. Development happens primarily on GitHub and at the W3C. Anyone can join and participate in the development. Ask me for more info if you're curious. And thanks so much to Kronos for hosting us here. Standardization updates, part of the big reason we're here, and I'm one of the chairs, so here it is. 1.0 is nearing completion. We're almost there. We thought we might have finished up next year. We didn't. So we're working on towards having it done in Q1 this year. WGL standardization has like a couple issues left. We're talking a little bit, this is like nitty-gritty details, but we're talking a little bit about some of the behavior when you do out-of-bounds accesses. We're adding opt-outs for uniformity analysis errors and warnings, which is a big feature request we've had a lot of. So hopefully that makes a lot of people happy. Uniformity analysis is still required in compute shaders, but that's how it goes. And we're looking at finalization of syntax for generics. Yeah, looking forward to generics in the future, even if the V1 of WGL doesn't have true generics, that we do have the pseudo generics like vec3 of F32, things like that. On the API side, we're also trying really hard to finish up, and we're burning down the remaining issues. We're still working on external texture for automatically sampling RGB primarily from video sources to keep overhead down when you want to pull in video content. Mess with it in WebGPU and keep that all on the video card, keep it all fast, keep it number of copies down to a minimum. We're also nailing down aliasing behaviors. So like when you alias data, what happens, what is guaranteed to happen and what is not guaranteed to happen, and is kind of left as optimization opportunities. And then other, minor final blockers for shipping our V1. This is kind of the last call for shipping features shipping in V1. We have a whole list of things we're going to talk about post V1 is what we call it. But V1 is closing soon. Implementation status in Firefox in Nightly, you can set a preference here, dom.webgpu.enabled to true and about config. Not really something you should browse if you want to be secure. This is something we want to give you to allow you to experiment. But we're working on being able to turn it on in Nightly very soon on Windows with other OSs to follow, and then shipping out to release closer to the middle of the year. Speaking of releases middle of the year, Chromium is looking to get WebGPU out and released in or around Chromium 1.13 later this year. So get pumped for that. Until then, there's still the Origin trial. Implementations are mostly interoperable already. So you should be able to work in both of them. Anything that doesn't work, file bugs with us and come talk with us. You can also use WebGPU outside of the browser. This is going to be exciting to half of you and uninteresting to the other half, but it's very available. It super works, and it's very exciting. And these slides are going to be available later, so I'm moving through them quickly for expedience purpose. We have a bunch of collaboration. We wanted WebGPU to be something that where we are best able to represent what people want and enable people to do all the things they want to be able to do. So to that end, we're working with a bunch of people: Three.js, Babylon.js, TensorFlow, Google Meet, MediaPipe, PlayCanvas, and Unity's down there at the bottom. Unity has some great collaboration that we did with them when they were looking at porting some of their existing shaders to WGL and dealing with our new uniformity analysis requirements. So it's really exciting to be able to work with all these cool people, and doing the things that we set out to be able to do is super exciting. And then resources, we have tutorials available. There's a number of tutorials that are great that we list here with some best practices in particular that Brandon's put together, which is really cool, and we hope to build out in the future. Hopefully we'll get a WebGPU best practices over to MDN at some point when we're closer to release. But for now, Brandon has a fantastic version of that. And then our samples, we have up-to-date WebGPU samples up on GitHub by Austin Eng. Those are fantastic, and we're actually hoping to be able to bring those more officially into the WebGPU repos soon and build on them. But for the time being, those are our gold standard. And contributing, many ways to engage. We talked about some of the channels for how you might reach out to us earlier. Matrix chat is one of the main ones that's listed in the slides. Try things out, see if they work for you. If they don't work for you, let us know sooner rather than later. We're super interested in feedback. Like this is our feedback phase. So we're never going to stop receiving feedback, but this is your time to make your impact and get your voice heard as we work towards a V1. And that's it for me. I believe I'm passing it over to Ricardo.
That's correct. Ricardo, if you want to take the screen.
Hello. Okay, I think that should be working now. All right. So I'm Ricardo Cabello. I lead the Three.js project, also known as Mr. Dev on the internet. I'm not going to detail too much. I will assume that most of the people already know what Three.js is at this point. So I'm just going to do a quick explanation of how we're trying to adopt WebGPU on the project. So as we've seen, like WebGPU is very likely to finally land this year. It seems like it's been a pretty long road until this point, but it's pretty exciting. And for the project, like for the Three.js, in our case, like we already had to do a transition like since the beginning. Like in 2010, when we released the project, WebGL was not released yet. So the render that the Three.js had was actually based on Canvas 2D. And then 2 years later, WebGL was released, and it took us like a bunch of years to transition from Canvas render to WebGL render, which the good thing was that somehow like we managed to keep the API the same. So with some like we had to add extra things for WebGL, but it was pretty successful to the point like the Three.js, like the API itself didn't have to change to adopt the new render. For the case of WebGPU, like now we've been working for already for like 2 or 3 years on a new render. In this case, will be a new WebGPU render. And if you go to the examples, you really can check some of them. We have like right now, like most of the examples are like pretty technical, so they're not the best representation of the kind of like the features that it has. But you can see a little bit of the progress that we have. Unlike, in fact, we have like some features that WebGL doesn't support at this point, like to be able to mix 2 backgrounds at the same time, for instance. And also, like most the screenshots still done The screenshots on the side, some of them still don't work, but it's still, yeah, it's all this stuff is still work in progress. But yeah, feel free to have a look at the ones that we have. Like we are basically adding as many features as we can to like reach parity to WebGL. So we have instancing, like some of the, like we started to add like license support, and some of the good things about like the new license system is that now we'll be able to specify like a material, we'll be able to specify which lights affect to each material, which is something that we were not able to do before. Like before, all the lights that were on the scene were going to be, you couldn't like select which one to apply. The goal is basically to try to keep it the same thing as, oops, it's a typo there. The goal is to try to keep it so in the same way as the canvas render to WebGL render transition, used to make it that's the only line that you will have to change on your code to keep it working. Unfortunately, there is in this case it's going to be a little bit more difficult because they're WebGL and WebGPU have like different shading languages. So WebGL has the GLSL, WebGPU has WSL, which means that we won't be able to keep some of the features that we had, or like some of the code that is like more advanced won't be able to continue working. So you, for instance, if you were using, like in the case of before compile, which basically it will be a material and you will be able to inject some GLSL code into it. As you can see, like the GLSL and like WSL code is pretty different from GLSL. So it will be kind of difficult to try to magically make that work without having to like include like a compiler in between and like bloat the library itself to be able to support, to keep working with the same code. We'll still try to like offer solutions for that, like to be able to show like if you still want to continue using that code, like to show how you can use a way of converting GLSL to WSL and like to provide some code for that. But for the most of the users will try to not like basically try to not use the before compile anymore. So the solution actually we try to do is like over the years, like Sunet has been working on this no material that it seems to, we never really got to make it the default on WebGL, but for WebGPU render, we're making it the default, basically the only option to do it. And that's going to be the transition to go from WebGL to WebGPU. So if you go to the example, you're really going to see some of the things that we have. Some of these ones are basically the same as the WebGL, but like instead of the non-material, basically it shows, you look at the code, it shows the what you need to do, or what would you need to do in order to inject some of the like different codes for it. Instead of having to do, yeah, this will be the example. Instead of having to do like before compile, it's much easier to inject specific code into parts of the material in a way that is not either GLSL or WSL. So the idea is that no material will produce GLSL or WSL depending on the render that is using, but it's going to be the same. It will be the same code, and it hopefully should be more future-proof. While building that, there's also we've also been building an editor for it. Let's find it. Notes. It's playground, where basically like if you're using like Blender, like you're already seen some of the, for instance, let's see this example. It's all combining, like you have the materials and you say the kind of you define with different pieces of code like how it's going to be, how it's going to affect the color, and in the end you end up with, that's how basically how you define the materials. But it's all like more visual based than not what we've been doing until this one, that it was only code based. You still can write it in code, but it's going to be much easier. Like used to give this to some artists that it basically gives you like a JSON, like you can export from it. You can export like a JSON file, of this material, and then you can use that on your scene. And that was something that we were working, also like over the last 2 years or so. But yeah, this will be like, for example, one of the JSONs that it outputs. But at the same time, we also found out about, last year we found out about this project called Material X, which it's made, but it's basically an open standard for representing materials, and it's made by Industrial Light and Magic, which you may know as I might like the people that the company that produces the VFX for Star Wars. And it's basically a very similar idea to what we were building for Nodes. But the difference is that they already have like a lot of like, compatibility with like, with Pixar, like Houdini, Maya, like Unreal Engine. And I assume I want to think that like several like vendor is also going to be adding support to this. So it's going to be, we thought it was going to be probably much easier to align to this node system. Like it's basically the same thing as a graph, basically a material defined with a graph, and then not try to replicate and build everything from scratch ourselves. So last year we already built, find it, like what they output is basically a XML file, and they have like a internally on like Material X, they have like also like a lot of definitions of this node produces GLSL, and this node produces these different shaders in different languages. So eventually I can think that they're also going to be producing WSL. So we're also going to try to align to this. So last year we actually built Material X loader, and you can find it also in examples. So starting with adding some of the nodes that they use for like creating noise. So this is basically loading one of their files, the XML files. And this is like one of the last one where basically you will define how, the width looks like in any editor, export it as Material X file, and then you'll be able to use it directly from the engine. And it will basically look exactly the same as it looks in Blender or Maya or Houdini or whatever you use for authoring it. Another interesting resource lately was this website called NodeToy. You can kind of see a little bit how it works, but it's basically the same kind of concept. But the idea is that you can create these materials from a website, and at the same time, what I find interesting is that there's already like a gallery of like materials that you can preview, or you can see how they look like and modify. You can fork them. And one example I had was here, say this one. So it's the same thing, you do it from a website, and this is how the material actually looks like. And the good thing is that from here, you can export that material. Take a little bit of time to, what was it? I think self-hosted. And then that material, you can export it as Three.js code, also like React Fiber, or like Three.js code. And this is similar. It's also like a JSON definition for the material. But like it just seems like everything is moving towards nodes, and kind of like leaving us like touching us a little bit from GLSL or WSL, and hopefully that's going to make it much easier for people to move from one render to the other render, like over the next years. So we're still going to have like, obviously we're still going to have a material that, you want to write like a shader material and you want to write your own custom shader, we're going to have an option for that. But for most of the people, I think moving to nodes is going to be kind of the way to go. Yeah, hopefully that's the plan. Let's see how this works. Thank you very much.
Okay, are you able to hear me?
Yes.
Perfect. Good evening, everyone. Hi. Thanks for letting me join you. My name is John Anderson, and I am a tech lead manager working on Google Earth for a bit over 10 years. And I've worked on Google Earth 9, which runs on web, Android, and iOS, Earth Pro on Windows, Mac, and Linux, Earth Studio, which runs on web, and a few other Earth products that are no longer under active development. Earth has almost a 2-decade-long history, so longer than I've been at Google. But tonight, I want to talk to you about just the last handful of years of Google Earth on the web. I think it'll be really interesting. So to get started, I want to jump right into a demo to kind of set the stage for this talk. And I tried to cram a lot into it, so I wanted to give you the TLDR of what to look for in this demo. So the first thing I'm going to do is search for Google Earth using a search engine. I'm going to click on the very first link, and it's going to load up the Google Earth app. I'm going to spin the Earth around and look at the imagery and the borders and the labels. Then I'm going to use the Google Earth time-lapse layer to visualize change over time. All right, let's dive in. So hopefully this video plays smoothly. So here I am, as promised. I've gone to a search engine and typed Google Earth, and I'm going to click on the very first link, Explore Google Earth. And this is the web application of Google Earth running right there in the browser. And I can spin it around, zoom in over Asia, see all the different countries and labels and whatnot. I'm going to zoom in this evening on Dubai and look at these palm-shaped islands. Now, Google Earth has over 38 million square miles of satellite imagery covering 98% of the Earth's population. So that's a lot of high-resolution imagery. But that imagery also changes over time. And so in the Voyager feature, we have this time-lapse layer, which lets you look at change over time on the planet at a planetary scale over the last almost 40 years. And so you can see that in the 80s and 90s, those palm-shaped islands were not there. They were actually built really recently in the 2000s. And with the time-lapse feature, you can actually see this sort of change over time and the whole planet. Excuse me, why is it doing it again? All right, so that short video showcased a few of the key pillars of what I consider to be important in Google Earth. The first is the widely accessible, easy-to-use product. The second is the high-quality data across the globe that we have, rendered very quickly. And the third is the ability for users to create their own dynamic data visualizations on top of that Earth canvas. And as I was preparing this talk, I realized that those pillars of what make Earth Earth would be a great framework for this talk. And so what I'm going to do is talk through the last handful of years of Earth development across these 3 dimensions of core technology changes that have happened, rendering and optimizations, and some of the content that we've delivered over the last few years. All right, let's dive in. So, core technology. I guess it all starts at that splash screen that you saw when I clicked on the Google Earth link from the search engine. You see this splash screen load for a few seconds. And the reason why it takes a few seconds is because it's actually a C++ engine compiled to WebAssembly. It's basically a video game for the planet that runs across web, Android, and iOS. While this screen is showing, we're loading the WASM module and key assets needed to draw the world. But if we rewind to 2017, we weren't loading WebAssembly when you hit Google Earth. We were loading a Pinnacle-based version of Earth that only would run in Chrome. It was multi-threaded, but couldn't run in other browsers. That's why as a team, we focused on building a WebAssembly version of Earth. And we launched that as we brought that to a beta in 2019 with and without threads. In 2020, we were able to fully switch to the WebAssembly version of Earth and deprecate the Pinnacle client. But if you rewind even further than the splash screen, that search engine result, earth.google.com, for many years, because we were Chrome only as an application, we couldn't direct to the web application when the user did a search for Google Earth. Instead, we would direct them to a marketing site. And then in the upper corner, there was a Launch Google Earth button. And if you clicked it with Chrome, it would work. And if you didn't, it wouldn't. And that was pretty sad. But in 2021, after that we were confident in WebAssembly working in all browsers, we switched it so the earth.google.com launches the app directly. And so this kind of brings us up to par with maps.google.com, for example, even though we're running a full WebAssembly render. So now I want to turn to the rendering and some of the optimizations that we've made along the way. And I'm going to actually go deeper than 5 years ago. I'm going to go all the way back to 2013. There was an internal email thread amongst my coworkers as we found out about ASM.js and Emscripten. And we were like, oh, I wonder if we can use this on our 3D render. And so I decided to go home that evening and give it a try. And the next morning, I sent out this email that had these 2 demos. It worked, but it crashed really quick, ran out of memory. And I even had the code and ran it this morning. I have the code just sitting on a internal site, and I loaded it up and it ran at 3 frames a second. So we've come a long way since then. In fact, between 2013 and 2017, when we launched Google Earth, a lot of work was put in on, how to make good use of Pinnacle, which then fed into how to work with WebAssembly. Lots of performance optimizations on how to load the app well, improvements in rendering quality, and the like. I wanted to focus on 2 of those optimizations that we've made. The first is in 2018. We enabled Brotli compression on the large web application files that we deliver. So that's the JavaScript UI, and then the at the time the Pinnacle binary, but then since then the WASM binary. And enabling Brotli compression, which compresses better than gzip in most cases, we were able to shave off 7 to 14% on the various files that we deliver over the wire to our users. Now, if we zoom in on this picture that I'm showing here, and what you saw as I zoomed across Asia in that video earlier, and you look at the text labels, and you see that it's not just Roman characters. There's a variety of different languages across the world, and being a global product, we need to render them all well. And this leads me to one of the next optimizations that we made, and this one actually Ken helped me with, Ken Russell. And together what we found was our C++ renderer needs to render these labels to render these labels, but we didn't want to package a full font or text stack in C++ because it would be too big and too difficult to maintain. So what our application does is we actually call out to a canvas in JavaScript and let the canvas render the text for us. But until we made an optimization in 2021, we were actually reading back the bytes of the canvas, shuttling the bytes down to C++ in WebAssembly, and then doing a texture upload to a texture that we were managing from C++, but that was actually in WebGL anyways, so back up to JavaScript. And the optimization that we were able to do was to just do a direct copy from the canvas to the texture and skip all the readback and re-upload. And this was a pretty significant improvement in jank and average frame rate across a large sample of Earth users. So good optimization, and thank you, Ken. And now I can turn to the third dimension that I wanted to talk about, which is content. And when I went in that video and I clicked on time-lapse in Google Earth, I was loading the content from our Voyager feature in Google Earth. And Voyager is a map-based storytelling and education feature that we launched in Google Earth 9. At the time when we launched it, we had stories about national parks and Muppets and wildlife conservation and a lot of other interesting stories. And since 2017, we've added hundreds of individual bits of content about, for example, where Google Earth has 3D imagery, and all sorts of other things. Sorry, Oliver, I can't help you right now. Zoom. We've also added the ability for Earth Engine to export tiles into Google Earth, and we've used those tile exports to drive a variety of Earth and Voyager layers. In 2021, we actually launched time-lapse in Google Earth, which I demoed earlier, and that kind of is the culmination of this Earth Engine-based tile export, because time-lapse is computed from Earth Engine. So I wanted to talk about that for a second. So time-lapse is the name of the data set that powers the visualization, the change over time visualization that I showed you earlier, where you can view 40 years of Landsat satellite imagery and take the playhead and set it to any year that you want, and then watch the change play back like a video on the planet. Time-lapse was computed in, as I mentioned, in Earth Engine, and then we exported it, and then we host it and visualize it in Google Earth. From about 2018 to 2021, we spent a lot of effort in improving our 3D renderer to be able to display these tiled geospatial videos in sync as the camera moves and as time changes. And before we launched time-lapse, between about 2018, 2019, 2020, we launched a few other features that kind of proved out that we were ready for this larger moment in animated clouds and visualizing polar ice and a few other stories within Voyager. And now before I move on, I wanted to also point out that in the Google Earth application, here highlighted in red, everything in red there is actually could be considered user-supplied content. It's not, quote unquote, native to the Earth application. We didn't build time-lapse and all these other Voyager layers into Earth. They're actually content that's loaded separately from the main Earth binary. And as a result, that whole UI there that allows the user to change the date is running in a sandboxed iframe. And over the years, we've had a lot of web security fun. I'm not going to make a timeline for all the various outages that we've had when we've screwed it up. So in closing, I wanted to turn to the future a little bit and just convey my excitement about a lot of the exciting new web technologies that we think could have an impact on Google Earth down the road. And this is, again, spans these dimensions of core technology, where we're seeing broadening support of WebAssembly, multi-threaded. We're seeing nearly universal support for single-threaded WebAssembly, even on mobile browsers, which is quite exciting. In terms of rendering and optimizations, we're excited for things like dynamic code loading, potentially making that splash screen even shorter so that we can get up and running more quickly. WebGPU, of course, is super exciting for its potential and improved performance and visual fidelity, especially where to support threads, which, as we know, Earth is multi-threaded. And then on the content side, there's various web security evolutions that we're trying to work through so that we can have that, user content and interact with the Earth app and make that really seamless and secure. And then other things like file system APIs that are becoming more standardized. Earth for many, many years was an installed desktop application on Windows. And so there's an expectation that users can do really robust local data management. And so some of these file system APIs are very exciting for that. So I want to thank everyone for letting me join this evening, and I hope that was educational, informative, interesting. I'd like to thank my colleagues at Google, especially on my team, and the collaborators across, for example, Ken and the Chrome team, and yeah, I think I'll close there. Thank you very much.
Hello. right, we'd like to ask the presenters to turn their cameras on. And Ken, would you like to take us through the Q&A portion?
Certainly happy to, and I hope that I have no more technical difficulties. All right, so everyone, please, don't be bashful. Please do ask questions. We're here to interact with you. So let's jump right in. So Brian asks, any hints at roadmaps for Unity and Unreal support of WebGPU? Well, we certainly can't announce or pre-announce any partners' products, so I'm afraid that we cannot offer any concrete news in this area, but if you go to Google and you search for Unity WebGPU support, you can find a very interesting thread on forums.unity3d.com on which a certain person who claims to be affiliated with Unity Technology says that a WebGPU backend is in active development. So hopefully you will find that to be exciting news. Okay. Secondly, Juan Tebaldo asks, can you please make the meetings earlier so it's not 2 a.m. in the Central European time zone? Thanks. Yes, we specifically scheduled this one to be APAC friendly, and so we're going to alternate the meetups to be European friendly and APAC friendly. So this is maybe one of the first APAC friendly Chronos WebGL WebGPU meetups. Hopefully that answers your question. Okay, let's see. Marco asks, question for browser vendors. Is there any plan to support GPU debug groups for WebGPU in DevTools, or overall have DevTools for WebGPU? Kelsey, you want to take this?
Yes. Yes. Yeah, I believe if I remember what we decided here was that this would be kind of end up being a UA style thing. I believe there are debug groups though as part of our push groups. If you see something that's missing though, please just like make a GitHub issue and like we'll either dig up what if something's already in the spec for you, or we'll take it into consideration and put it on the roadmap. Thanks.
Also, the browser implementers definitely want to make WebGPU debuggable. No question about it. It's not just going to be an API that we toss over the wall and say good luck. So please do look forward to more developer support tools from us in the near future. Okay, so let's see. The last one that's currently in, and please, folks, don't be bashful. If you have any question for one of the Earth architects, or the Three.js lead, or the WebGPU co-chair, please do ask. For the arbitrary HTML and CSS in WebAssembly and Google Earth, is this a technique other developers can do in their WASM apps? Is there a blog or a resource that you recommend? John, do you think you could answer this?
All right, so sorry, just so I clarify, the questions about the web security blurb that I mentioned about arbitrary user content. Is that right?
That does seem to be what the question is about, yeah.
All right. Yeah, so a little bit more context there since you asked, thank you, is that Google Earth supports a format called KML, which is the keyhole markup language. It's the long-term format of Google Earth back to 2005 when it first came out. And in KML, it's an XML-based language, a spec, and it basically describes a geospatial document. And on any feature, a user can make what's called a balloon, which, historically you had a point on the map. You can click on the point on the map and up pops a little balloon that displays some content, often like a description of a place with a photo, or, could be anything. And that was the beauty of KML, was that it could literally be your heart's content. It was just arbitrary, basically arbitrary HTML. And Google Earth would, as a desktop product, we popped up a little web view in Qt and drew whatever the user specified in their document. And there's some amazing KMLs over the years of all the things that people did with that power. And we've tried to bring that to the web and still allow that. But of course, that means that we have to we have to make an iframe, we have to sandbox it, we have to not let it touch, you know, and pretend to be Google Earth and then touch other products. And so I think a lot of, you know, it's certainly something that can be done. There's a lot of care that needs to be taken as you embed effectively foreign content in your application, but it's definitely something that brings a lot of flexibility for our users.
John, if I could maybe follow up a bit, did you have to define like a really well-defined API between the main application and the sandboxed iframes to give them some ability to, you know, work with the Earth view, but still say?
So we actually have a fairly narrow API around the features. So for example, a balloon can toggle the visibility of the feature that it's associated with, or it can fly to another feature within the document. For the time-lapse example, that scrubber, you can actually set the frame, the target frame of a ground overlay, which has the video tile associated with it. So that scrubber is implemented as basically a seek in a video on another KML feature. So there is a pretty narrow API that allows the balloon to talk to the application and the application to talk into the balloon bidirectionally. And that's, yeah.
All sounds great. Thanks, John, for the answer, and thanks, Omar, for the question. Next question, Gonzalo asks, do you know React 3 Fiber? What do you think about it? Ricardo, have you ever heard of React 3 Fiber? Do you think you can answer this question?
I hear about it sometimes every day. So React 3 Fiber is basically like a framework, I guess, on top of Three that basically brings React composability on top of the imperative nature of Three.js, which allows anyone to basically use React and combine, like create and scene use, you know, by moving in a way like similar to if you were using HTML around, like you define the scene with React, and it has basically allowed like a new ecosystem of like people building components in a way that is much easier to create components, iterate, and create 3D experiences than not in Three.js. But it always is, you know, it's a different kind of mentality, but it basically suits much better for people that really know React, you know, compared to people that use JavaScript. But I think it's pretty exciting myself. But in the context of WebGPU, yeah, I'm curious to see how that transition is going to go for them too. We're gonna have to look into that for the next years.
Okay, great stuff. Thank you. And let's see, going on. Leanne asks, what are the benefits of moving to WGSL as a shading language for WebGPU? Kelsey, would you like to field this one?
Yeah. Man, we talked about this one for quite a long time in the working group. There's a lot of discussion about what to do here, and a lot of input that eventually ended up in us choosing to make WGSL more or less from scratch. It's hard to point to like particular concrete benefits outside of the context of what someone is looking for. I think some of the benefits that we were looking for definitely as implementers were things like ability to read it and parse it in a way that's not ambiguous and not too difficult to implement, and then also to have primitives built into it such that we can reliably and faithfully translate your developer intent from our input WGSL to HLSL, to GLSL, to Vulkan, to metal shading language, all of our various backends, and the different versions within those that we have to support. So that's one of the main benefits to us as implementers. To users, it depends a lot on what you like to use. We like to think, and we've had some good feedback that we're giving developers useful tools in WGSL. We got some really good feedback from people who are used to having to write very verbose code, suddenly being able to skip over writing types because we have some degree of type inference in WGSL. And that makes it so you have to type vec3 a whole lot less often, which a lot of people are enjoying. And we're also giving people uniformity analysis, which is a really kind of neat thing that FXC, the D3D compiler, used to have some degree of. We're kind of doing something maybe similar to that, where we're calling out and detecting when you have things in your code, in your fragment shaders, where you have non-uniformities that happen, that many languages like SpearV just sort of say like, well, if you violate this contract, you might get what you want or you might not. And you might run on your machine and might work on your machine, then you run it on someone else's machine, maybe it runs on a phone suddenly, and it doesn't do what you expect anymore. One of the tools that we're giving developers and authors is the ability to know that ahead of time and be able to make it so that it's much more reliable and your thing will actually just work everywhere, even as we add a lot of flexibility to this language in contrast with WebGL. That's my short little overview.
Sounds great. Thanks for the question. Thanks for the answer. Okay, Anonymous asks, is there a recommended way or tool to debug which objects are uploaded to memory which are not JS objects and how much each object or resource is taking, like textures and shaders? So Anonymous, you didn't ask whether you were talking about WebGL or WebGPU, maybe both. There are a bunch of different tools and libraries that can help you with this. One, if you search for WebGL-memory, our teammate Greg Tavares, on request of one partner, just put this together, and that will give you a good approximation of the retained GPU size of the allocated textures and other buffers in your WebGL context. Different user agents have different support for this in their own memory profiling tools. Chromium has a certain degree of this in its internal tracing, which you can get to with about::tracing. There's a memory infra type trace that can actually get you more of this information, a deeper level than DevTools can. Kelsey, since you work on Firefox, any feedback on what's supported there?
Yeah, we have supplemental notes in our about memory support. So about memory is like the general thing you use in Firefox to be able to see what's taking up memory and where it's coming from. We have some supplemental notes in there. It's not something that's maybe extraordinarily easy to use. And we've had some reports where it's not maybe showing exactly everything that's being allocated, but like that's where you would find it. That's where you would look for it. It's about memory in Firefox.
Okay, hope this answers your question. Please feel free to follow up. And Kronos folks, I hope that we can maybe run a little bit past the hour since we got a late start. My fault, sorry.
No problem at all.
Great. So Alex asks, is there a roadmap for WebGPU ray tracing? Will it be shipped as an update to WebGPU in the future? So one thing I can say definitively is that large features like this will be added as new extensions, new functionality, so that you'll have to query for its support and enable it somewhat similarly to how WebGL extensions work. And I'm also aware that there are some pretty significant portability issues between the various low-level APIs support for ray tracing, and defining a portable interface is really the challenge here. But Kelsey is more of the WebGPU expert, so would you like to comment on this?
Yeah, it's not on the roadmap other than like we have issues filed for it that are marked as post V1. So after V1, we're hoping to look more into this. And so I don't have something specific on a roadmap for it, but part of that is because we don't have a roadmap past shipping our initial version so far. We have kind of a soup of things that we're going to look at afterwards that include things like ray tracing. You should expect it though. Like you should expect WebGPU to pick up ray tracing in the future here.
Okay, okay, great question, great answer. Alexander asks, any updates on the base for text-based instance extension for WebGL and Chrome and Firefox? So this has been debated for quite a long time in the WebGL working group, and the primary concern is that we want to make sure that it's going to be a performance benefit for end users. Right now we have basically one use case from one partner, and the performance results were a bit inconclusive. We don't know whether we may have messed something up on the Chrome side, for example. I think that Firefox renders the same engine much more quickly than Chrome just in default mode, and I don't know why personally. But finding like the sort of conclusive proof that that it's going to be faster is what we're waiting for. This has somewhat been on me to write the test case that, you know, accumulates a bunch of similarly sized objects in the same buffer and then uses this thing to just draw them all on the screen and prove that it's faster than even the multi-draw extension. If you can help with this, if you have a small standalone test case and can, you know, add a couple of arms in it that do, you know, regular draws and using this extension and can show us, yeah, look, there's really significant speed up, that would be great. We'd really appreciate it. We'd love to check it in somewhere as an example, and then use that as motivation to get this thing out of draft and community approved.
On the Firefox side, I can say that I think we're expecting to implement the non-multi-draw version of this, and we'll probably end up implementing the multi-draw one too. We had more concerns about the multi-draw version than the regular draw instance base vertex base instance thing. But yeah, stay tuned. I think it should show up.
Okay, going on. Brian asks about WebGPU's release dates. Kelsey, you want to go first? Take a crack at this.
Sure. Yeah, 1.13 is for Chromium. Maybe I said Chromium. I think that is Chrome. That is the planned release version for Chrome as it stands today. You know, it's not incredibly final. Like, don't tie all of your ships to that, because it can still get pushed back, right? It has to go through beta. It has to roll out to release, and we have to make sure. I mean, really, more Chrome has to make sure that it's good as they roll it out. But that's when you should expect it, more or less, like 1.13 or within a few after that for Chrome. And yeah, May 2023 that's the right timeline. For Firefox, we don't have a designated release like candidate version yet. It's probably going to be after May, but it's going to be this year. So I'll let you know when I know better when that is, but sometime around the middle of this year is what it feels like right now. I believe Edge is following Chromium here as part of like the Blink family of browsers, and so I believe that Edge should be picking it up like on a relatively similar time frame as Chrome, but don't quote me on that. I don't know exactly when they're releasing, but that's my expectation. And Safari doesn't comment on future products and roadmaps, so I'm not going to comment for them either, unfortunately.
Okay, but it all sounds good. Hopefully that answers the question. Okay, moving on. James asks, there were some tutorials mentioned in the slides, but any additional recommended learning resources for WebGPU and WGSL? Kelsey? The
tutorials, I think. The tutorials and the samples. Like the samples are relatively straightforward, I think. Sometimes I know how samples can be sometimes, where sometimes they're really not very readable code. I think the samples this time around are like relatively readable, and you should treat them as like, this is kind of like our intent in WebGPU is that either the current form or a future form of these samples will be like both us showing off what it can do and also us demonstrating how we would write it and how we want you to write it. So look for both those things in there. So if you read better by reading other people's code, samples, if you read better, but if you learn better by doing, tutorials, I think is the way to go.
Okay, sounds great. Moving on, Matthias, I think, has a question for John regarding Google Earth. Could you elaborate how you're using WebAssembly there? Is it used to provide inputs for WebGL programs, or in some different way, like providing raw pixel data to WebAssembly to render?
Oh yeah, thanks for the question. I mean, think of Google Earth as a whole. The C++ kind of video game engine part of it that I mentioned is well over, I'd say 90%. You could ballpark it at that, and then the JavaScript part that is the application UI is the remainder. So that's kind of a breakdown guesstimate. For the C++ part, the 90%, that's just a pretty classic like 3D renderer that downloads data from our servers in a tiled way, unpacks it, preps it, and from its perspective, it's thinking that it's talking to GL.h, like as any C++ computer graphics program that uses OpenGL would. And then we use Emscripten's headers and compile them Emscripten to make those GL calls that C++ is making actually individually go out to JavaScript and execute in WebGL. So nothing crazy. Basically just a C++ game engine for rendering the world compiled using Emscripten.
Super. All right. Thanks, John, for the answer, and Mateus for the question. Great to see that more questions are coming in. All right. So Anonymous asks, is it the same situation like ray tracing for features like multi-draw indirect and other common features that aren't currently found in WebGPU? Kelsey?
Yes. Like expect them to show up as features that will be like that you can test for. But it's hard to say exactly what form they'll take. But our goal is to like offer you the features, and they should be pretty similar. Like it should be features on top of the language. It's not going to be like a new like WebGPU ray tracing API. We're not going to start from scratch like that. It should just be features that are added to features. Capital F features is our name for extensions, I think, in WebGPU.
Okay, sounds good. Moving on, Antonio asks, is there a specific reason why WGSL syntax diverges from C-based languages? Ricardo already mentioned the complexity that this brings in terms of interoperability.
Right. There's kind of trade-offs in what we want to do. When you go for something that's extremely C-based, you pick up a lot of the struggles that C has in terms of parsing and lexing that other approaches and other languages don't have. And so that's part of what pushes us away and has pushed us away from some of the way C does things. You can see that in terms of how we picked up a kind of a Rust-like way for type definitions, where you do like var space identifier colon type instead of the more C-like way of doing that. And it can be a little frustrating. It's not something that we feel takes a lot of mental effort and becomes second nature very quickly. So we're not very worried about that. And we expect a lot of people are going to be using type inference anyways. But the baggage that being extremely C-based brings is maybe one of the headliners for why we don't try to be as C-like as possible.
All right, great answer. Good question, thanks. Okay, Renaud asks, how will the new extension shader pixel local storage improve performance? It looks very interesting, and can you provide a concrete example? Well, without divulging any company proprietary information, because I don't know what is proprietary, Chris from Rive, you can look up rive.app. You can see the product that they build. It's an animation engine. And let me just say that Chris demonstrated some dramatic performance improvements with doing vector rendering on the GPU hosted on top of an OpenGL API and using pixel local storage versus not. The amount of anti-alias, so analytical anti-alias blending you can do with custom blend modes using pixel local storage versus doing it as successive draws to the back buffer, needing to sort of ping pong between two frame buffers it's beyond what I had comprehended personally. So just be very, very excited about what you can do with this if you have the right application use case. And I'm sure that Rive will have some awesome stuff for you to use on top of it as soon as it's on the web. Anybody else want to comment here? Okay, thanks for the question. Let's see, Leonardo asks, any idea of the difference between WebGPU and Three.js's WebGL backend in terms of rendering performance limitations? Ricardo?
So we are still architecting, like building the renderer itself. So we haven't reached the point where we're doing performance comparison. But my expectation is that, like the amount of triangles is going to be the same amount of triangles that the GPU can handle. But the actual result is that it's going to be using less CPU. So the performance is like less CPU usage, and it's going to be like easier to also for browsers to deal with it. But performance should be visibly similar, I think. But we haven't reached that point yet.
Okay, this is good to know. Let me highlight. We've worked with another partner on their WebGPU backend for their rendering engine, and they were able to put into production some of WebGPU's new features that aren't available in WebGL, like render bundles. And this allows you to re-execute a bunch of draw calls, previously recorded with very, very low CPU overhead. And they were actually able to drive up the rendering performance pretty significantly from their WebGL renderer. Now, I do hope that some of the recent extensions that we've implemented, like multi-draw, will allow you to take your existing WebGL app and raise the performance bar. But still, we're pretty excited about raising the performance ceiling dramatically for WebGPU and getting a lot closer to what you can do with native applications. So the future is bright. Okay, with that, it kind of looks like we've tailed off on the Q&A. So shall we hand it back to the Kronos group?
Great. Thank you for the wonderful presentations. We truly appreciate your guys' time and effort in putting together today's meetup. As a reminder, a recording of the presentations along with the slides will be available on the Kronos Group website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to help us improve these presentations. Please let us know if there are other Kronos-related topics you may be interested in, and thank you for joining us, and have a great day.